Hey everyone, Jason from OrganicChemistOnCall.com again. As you can see in the title here, I'm going to go over free radical addition of hydrogen bromide to alkenes. So what I first want to go over here is we've seen alkenes with the addition of an acid, and what we've seen is what's known as a Markovnikov addition. We get the bromine on the more substituted, the hydrogen on the less substituted, and we've seen that that goes via carbocations, so we always want to look at the stability of the carbocation. So when we think of double bonds, typically in the presence of acid or some of the reagents that we've seen, we think about a double-headed arrow where we're going to move the entirety of the electrons of the double bond to one side versus the other. As we can see here, we can get two different structures. And as we've talked about, the one on the left, the red one, is going to be the preferred one because that's the more stable carbocation. So this, as I said, is in the absence of peroxides. We get a double-headed arrow. Now when we have it in the presence of peroxides, what we're going to be using is single-headed arrows. And this has to do with radicals. So we can imagine instead of moving both electrons to one carbon, we move one electron to each side. And now we think of single electrons. So we can see that we don't have a charge here, but we have to deal with the electrons themselves. And if we look at these two here, we're not going to be worried about, as the example that we have up here, carbocations, but radicals. And as you probably all know, radicals follow the same stability as carbocations. So in this case, the more substituted, the more stable. So if we look at this mechanism specifically, what we're going to do here is the initiation of this reaction has to form some sort of radical. So what you're typically going to have is some sort of bond that's symmetrical. Typically it's going to be a peroxide, where you're going to have an oxygen-oxygen bond. Those are very easy to break under heat or light. So once we break that, we can see that we wind up getting two oxygen radicals. Now this radical, as we saw before, when we have radicals, we have to do single-headed arrows. So what's going to happen here is the electron from the oxygen is going to interact with the hydrogen bromine bond, but what we're going to do is pull one electron out of the hydrogen bromine bond and form it to the electron on the oxygen, and then we're going to push the other electron, or we could say it's going to stay on the bromine, and what that's going to do is generate an alcohol. But you can see throughout this, just like with carbocations, when we do mechanisms, we move the carbocation from one atom to another. In this case, we're going to be moving a radical from one atom to another. So here we formed an alcohol, but now our radical is on our bromine. So now we're going to take this, and this is going to interact with our double bond. So we could imagine taking our double bond, taking the bromine, interacting it on the left-hand side, pushing the electron out on the right-hand side, and that would give us this intermediate here with a primary radical. We could also imagine taking the bromine and going on the other side, taking one of the electrons from the double bond and forming a bond with the bromine, taking the electron, dumping it on the other side, on the right-hand side, and that would give us a tertiary, more substituted radical. So as we talked about before, these are going to follow the same stability as carbocations. So the one on the left, or sorry, the one on the right, which is tertiary, is going to be the most stable. So now that we've identified that, now we can finish the mechanism. So at this point, we've got that radical on the secondary, I think I said tertiary, as secondary radical, secondary position. That will interact with the hydrogen. So one of the electrons from the hydrogen-bromine bond will interact with the radical on the carbon. We're going to dump the other electron on the bromine. That's going to give us our new bond. And you can see that at this point in time, we've got our anti-Markovnikov addition. And then what's unique about all of these, or not really unique, but what's important about these mechanisms is that when you do your reaction, and this is, didn't go into the details here, but you can look in your book, or you probably know that there is an initiation, a propagation, a termination step. And this, in the propagation step, once you've actually formed your product, you always want to make sure that you generate a radical that then can be used to go through the entire process again.